Okay, so we've been talking about the Aldol condensation reaction. We've said that this is a reaction that is both a chapter 19 type nucleophilic acyl addition reaction and a chapter 22 type deprotonation alpha-2-carbonyl reaction. So it's both of those ideas put together. And we've only been looking up till now on regular, you would almost say non-mixed aldol reactions, in which the two molecules that are reacting partners are two molecules of the same thing. And we discussed how if you started with cyclohexanone with some base, this reaction is base catalyzed actually, then you would get at first an initial adduct that looks something like this. And if you were very careful with this compound and kept it nice and cold, and certainly didn't let it near any breath of acid, you might be able to isolate this. I've not done too many aldol reactions in my life, but these beta hydroxy ketones and beta hydroxy aldehydes are pretty unstable. They do like to undergo dehydration in order to form a new carbon-carbon double bond that's conjugated to the carbonyl. And I also want to review how in some cases, no matter how careful you are, you will not be able to prevent that dehydration. And I know students today don't much like things that aren't 0% or 100%, but I'm afraid I can't give you that. I would say 90 to 95% of the time, it's going to dehydrate. Certainly you could force it to dehydrate. We'll go over that again today as well. But those cases where the driving force to dehydrate is so strong that you can't prevent it no matter how much you might want to, we'll go over that. There's going to turn out to be a good reason. In general, in science, there's a good reason for things. You know, even things that seem like exceptions, which we're going to get to one today. There's generally a good reason, and we might not know it yet, but in general, there's a good reason. And happily, the things we're going to look at today, we do know the reasons. Good. So the dehydration process, I think we've already gone over this, is going to be neither E1 nor E2. It goes by an E1CB mechanism. So again, if you've forgotten about the E1CB mechanism, please go back and review that in chapter 11. And indeed, in cases like this, you don't even really need to do anything special to the reaction mixture. But I would predict all you'd need to do is heat it to some degree. And that would give enough energy to get over the barrier and do the dehydration. But it goes through an E1CB mechanism. How can you know when an E1CB elimination is going to happen? Well, generally you want at least one of two things. You want either there to be an especially acidic proton, which we know is going to be the case. That proton is alpha-2-carbonyl. So that's much more acidic than your average hydrogen attached to your average carbon. That's going to make the pKa be, probably somewhere in the 20s, mid to upper 20s, as opposed to, 60 or 65, which would be, let's say, the protons that are on that CH2, for example. Those are not acidic at all. So it's a very dramatic difference. It can be 40 orders of magnitude. So that's one thing is you want, if possible, there to be an especially acidic proton, or you'd like for the leaving group to be somewhere between mediocre and even awful. You want a poor leaving group, mediocre at best, to favor an E1CB mechanism. Why? Because in the E1CB reaction, the loss of the leaving group is the rate determining step, and it happens second in favor of deprotonating first. And no wonder, because that proton is going to be especially acidic. And with it being set up so that it's going to be next to a carbonyl group like that, that's going to be an unusually acidic proton, at least in a CH bond. So you want either an acidic hydrogen, so you can deprotonate first, or you want the leaving group to be mediocre at best, or both, which is what we have here. And so small wonder that it goes by an E1CB mechanism. And So the mechanism starts with deprotonating. So we'll use whatever base is in our reaction mixture. Again, remember, and I know Owl is strangely fascinated with metal ions, but remember when you see something like Ch3ONa, it really is this. It's the methoxide ion. I'm still seeing too many metal ions or alkali metal ions used in reaction mechanisms. They play no role in the chemistry here. They just are counter ions. They're just spectator species. So you should never, ever draw any metal ions or oxygen metal bonds or anything like that. Certainly not with alkali metals. So those are not going to be involved in any mechanism. I don't think you've ever seen me use an alkali metal ion in a mechanism. They're just spectator ions. They're just there to balance out the charge. Anyway, whatever the base is, in this case methoxide, any other base would do, any other reasonably strong base would do. We're going to pull our proton off first. Recall in the E1CB reaction, we deprotonate first. It's turning the E1 reaction exactly on its head. In an E1 reaction, we lost the leaving group first because in order to generate a carbocation. So that's the exact opposite of this. Here we deprotonate first. And again, not surprising, we have an especially acidic proton. So we form our enolate, and I'll remind you, enolates have at least 2 good resonance forms. So you don't have to use this resonance form if you don't want to. Remember our rules stated many times for reactions that have intermediates that are resonance stabilized, which is not rare. Here's an example of something like that. Remember that in cases like that, it does not matter which resonance form you use. If you would rather draw the resonance form with the carbon-oxygen double bond still there and the minus charge in carbon, go for it. Again, if Chef John of Food Wishes were here, he'd probably say something like, you are the Alexander the Great of your enolate. You're the boss of your sauce. If you want to use the other resonance form, you'll find there's a correct way to draw the mechanism that way too. I generally put the minus charge in oxygen. Some students like to do that, others like to put it on carbon. So whatever works best for you, as long as you draw the mechanism correctly, it's fine. In general, you don't have to draw all the resonance forms unless it specifically says to. Cough, owl, cough, you know. But if it doesn't say to draw all of the resonance contributors, don't. Pick whichever one you want. And you should find there's a perfectly valid way to draw that mechanism. So, but the first step is the proton transfer. And remember, proton transfers are always extremely fast kinetically. Always, no exceptions. They're the fastest type of mechanistic step there is, wheresoever they may occur, whether in the lab, whether in living systems. Proton transfers are always extremely fast. Good, so you pull off the proton to get your enolate, and then that enolate decomposes and kicks out hydroxide as a leaving group, which again, hydroxide's a pretty bad leaving group. We certainly would never lose hydroxide in a neutral to acidic solution, but in an alkaline solution, it's good enough. And so you can see we've dehydrated, we've lost the elements of water. We've effectively lost H plus and OH minus. And so technically, yes, you will get 1 molecule of water for every condensation reaction that we do, but that water is going to be a non-factor. It's going to be swimming around in this ocean of, in this case, methanol. And so it's a non-factor. It's not going to play any role in the reaction. And while we're at it, in addition to getting a molecule that looks like this, in cases like this, I'm just making you aware of this in case you run into it on OWL, I would not be surprised. Remember, there's still a set of acidic protons on the other side of this carbonyl over here. So that's pretty common with a lot of these ketones. So I would not be surprised if under the same reaction conditions, we also deprotonated here, formed that enolate, and had that attack yet another molecule of cyclohexanone and then dehydrate. So you'd wind up with 2 ears or 2, I don't know, horns or something going on over here. So I would not be surprised if you actually got 2 of them. You'll know by how the question's phrased. right? Right. In general, it will give you the product to aim for, which is exactly what we did not do at my previous school. We did an Aldol lab, and it was one which the good part was they were all reactions that were destined to dehydrate. You could not possibly keep it from dehydrating if you wanted to. And they knew that, but what we didn't tell them is you got a double condensation like this. So those poor kids hated us. But yes, so I wouldn't be surprised if in fact you got that type of product at the end that had undergone 2 condensations. And once you've done that, you're done, because there's no more acidic hydrogens, right? These remaining 6 protons are not acidic at all. So watch out for that possibility. I would not be shocked if Owl threw one of those at you. Good. Now, what about that dehydration? Well, we said last time, I'm still essentially reviewing what we did the last time, and I don't mind doing it. We still have 2 more classes to finish chapter 23, and it's plenty of time. I am in no mood to rush through this. So, what do you want to look for if you want to know whether you're looking at a case where the dehydration is going to happen regardless of what you do and you can't even prevent it? Look for cases where the dehydration gives you a conjugated extended pi system. So there's going to be a huge driving force to lose water if our starting material is, let us say, acetophenone, because in so doing, this carbon-carbon double bond not only is conjugated to the carbonyl group, but it also forms an extended conjugated system all the way through both benzene rings. So all of those carbons are sp2 hybridized. That whole part of the molecule, including the oxygen, is flat. It's all planar. And you've got pi electron delocalization all the way through the molecule. And the only thing getting in the way is essentially this water molecule, the OH and the hydrogen. So this is a case where you couldn't prevent it from dehydrating even if you wanted to. And even in cases like this one here, I would predict you would only need to heat it a bit, and it would spontaneously dehydrate, even under the reaction conditions. If you didn't heat it up, if you kept this initial adduct nice and cold and treated it with lots of care and respect, maybe you could isolate it. But in general, it's difficult to isolate those things. And in cases like this, where you get a conjugated pi system, you can't. You can't even prevent it. You couldn't prevent it from dehydrating even if you wanted to. So that would be a good one for you to work out the mechanism on your own in terms of both the aldol condensation reaction and the dehydration. I'll also just point out, you'll notice that I've here put let me get this right. I guess the alkene would be the E alkene, wouldn't it? Because the benzene ring is trans to the carbonyl group. And I'm pretty confident in predicting that you would get that, because that's going to be more stable than the Z isomer, in which the 2 bulky benzene rings are on the same side. So I think in cases like that where it dehydrates, you can feel pretty confident predicting that the major product is going to be whatever is the most stable of all possible alkenes. And I think I'm on pretty solid ground in expecting that the Z alkene will be much more stable. The E alkene will be much more stable than the Z alkene. I have no excuse since I took German in high school and college. So, so much for that. That's pretty much where we ended the last time. Questions so far? And again, all this is in your class notes. Everything you see displayed in the class notes is already in your class notes. Hopefully it all kind of rings a bell. Well, what if, though, we didn't want both reaction partners to be the same molecule? 2 molecules of acetophenone, 2 molecules of cyclohexanone, 2 molecules of acetaldehyde, whatever. What if you wanted to react 2 different molecules and do an aldol condensation? Well, this would be a fool's errand if both of those 2 carbonyl compounds have acidic protons. If the 2 molecules are A and B, then you're going to get A reacting with B. You're going to get B reacting with A, which is different. That's a different condensation product. You'd get 2 A's reacting, 2 B's reacting. It'd be a mess. So that goes against all ideas of best practice to use two different carbonyl compounds that both have acidic protons. There are some ways, there are strategies you can use to get mixed aldol reactions that are clean and give you just one product. One of them is just to pick one of the two reaction partners such that there are no alpha protons, like benzaldehyde is this way, right? There's no acidic protons, alpha to the carbon, there's no protons, period, alpha to that carbonyl oxygen. And certainly coming off a benzene ring, they would not be particularly acidic anyway. But especially since if you tried to put a proton on, you'd get 5 bonds to carbon. So we got a problem. There's no acidic protons. And any way you might do that by not having any acidic protons should allow you to get a clean reaction. It will ensure that only one of the two reacting pairs can get deprotonated. The other one cannot. So the one that gets deprotonated will surely only act as the nucleophile, and it's the other one that will act as the electrophile. So the one that gets, or you could say the one that gets deprotonated is going to be your donor of electron pairs. The other one is going to be your acceptor, right? Your Lewis acid, your electrophile. And so in this case, I would predict the benzaldehyde would act as the acceptor, and the 2-methylcyclohexanone will be our donor. This is an interesting case on top of it, because you'll notice that I've put in your class notes, I would predict that you would get the product from, that results from deprotonation in the less hindered, the less hindered position. In other words, deprotonation at the kinetic site, even though we're using a thermodynamic base. And I think there's a very good reason that we can expect that. So I would predict that this would be the major product by far. I don't think we'd get any significant amount of this one. And unrelated to that, but also bearing pointing out, you'll notice once again, I've drawn the, let me get this right now, the E alkene, right? The benzene ring is trans to the carbonyl group. And I predict that would be significantly more stable than having the benzene ring be cis to the carbonyl oxygen. So I'm very confident predicting that's going to be the major product and not the Z stereoisomer. But certainly that compound will also far overshadow any, I don't think you'll get any detectable amount of this product, only that one. So that's something for you to think about for a few minutes. See if you can work that out. That would not be a bad thing for you to work out that mechanism, and also to convince yourselves why you get this instead of this. Why we're going to deprotonate preferentially in the kinetic deprotonation place rather than here in the thermodynamic deprotonation site. And again, I'll let you know, I'll even give it largely away. The ethoxide ion will most certainly deprotonate here too. Absolutely, it will. I'm just saying that's not going to lead to a stable product. Instead, you will get a stable product by deprotonation at the other site. Call it an exception if you want to, but I think there's a very good reason for it. And this is another good example for us of, in science, when we see things that at first look like exceptions, there's generally a very good reason for it. We might need to modify our theory a little bit, or we might not know at first why that thing happens. But in general, there's going to be a good reason. And I think you guys will get it. So my point here being, there's two ways to make sure that a mixed aldol reaction, which I've here defined in the class notes, there's two ways to make sure that that reaction is clean. One way is to make sure that one of the reacting partners has no alpha protons. Then it's clear. Then you'll get just one product. The second way is to make sure that one of the reacting partners has a set of alpha protons that's especially acidic. And you could do that, for example, by treating cyclohexanone with our old friend, that's ethyl acetoacetate. You probably remember that compound from chapter 21, 2, I think, right? We talked about the acetoacetic ester synthesis, for instance. And so recall that these two protons now are between two carbonyls. They're alpha to both the ketone carbonyl and the ester carbonyl. And if you need to draw out that ester group to convince yourselves of that, that would be fine. But these two protons are especially acidic, much more so than the protons in the methyl group, much more so than any of the 4 slightly acidic protons in cyclohexanone. I would predict that these 4 protons and the 3 on the methyl group here, all of them alike. I don't have these absolutely committed to memory. I should. I expect myself to have these somewhat nailed down. I don't know that I would expect you to have this quite so well memorized. But if I had to guess what the pKa's are here of these two CH2s and that CH3, I would guess it would be round and about in the mid to upper 20s. 28 would not surprise me. Whereas these two here, I would predict would be more like in the low 20s, maybe even 19, maybe even 18. So, I mean, it could be a difference of 10 orders of magnitude. It's not a small difference. So naturally, when we mix these two together in some base, I'm just using sodium ethoxide and ethanol as an example. There's any number of other bases that you could use, but I would predict this will deprotonate cleanly between the two carbonyls to make exclusively this enolate. And actually, this enolate is no fewer than 2 other resonance forms. Here I drew the minus charge on the ketone, what had been the ketone carbonyl oxygen. You could also have drawn the minus charge on the ester carbonyl oxygen, or what had been that oxygen anyway. And then the carbon-carbon double bond will be here. Or you could put the minus charge in carbon. Any one of those 3 will work out just fine. There's corresponding correct ways to write that mechanism using any of those eventualities. So you should use whichever of those 3 resonance forms you like, whichever makes it the easiest for you to learn. But whichever way you draw that enolate, that's now going to add to our cyclohexanone molecule. Because we're going to make sure, by virtue of those 2 protons being especially acidic, we're going to make sure that your enolate only forms on the ethyl acetoacetate. That then will add to the cyclohexanone. It's not going to add to another ethyl acetoacetate molecule because those molecules will largely have a minus charge on them already. They're not going to want to act as an electrophile. They want to act as a nucleophile. So this attacks the cyclohexanone. And then just like before, I think you would at most have to heat the reaction mixture mildly. And mild heating might even just mean warming it to room temperature, since generally these things are done pretty cold. But the first thing is going to be putting the proton back on this alkoxide oxygen using whatever the solvent is that you're given. Don't memorize that ETOH goes here. It might not. It depends on what you're given. Once you've done that, then we're going to do our E1CV type elimination again. First, we'll pull off, in this case, the one remaining proton that's alpha to both carbonyls. And you could put the minus charge on this carbon, you could put it on this oxygen, or you could, in fact, put it on the ester oxygen. Whichever of those 3 you like. You're the boss of your sauce. Once you form the enolate, that's then going to decompose. Just be sure you draw the mechanism correctly. But for all 3 of those possibilities, there's a correct way to draw that step. We lose our hydroxide ion, which is a mediocre to poor leaving group, but in basic solution, it's good enough. Acidic neutral to acidic solution, no way. There's no way you could lose such an alkaline leaving group in neutral to acidic solution. Alkaline solution, you can rationalize it. And so in the end, I would expect you'd get this tetra-substituted alkene product in which the carbon-carbon double bond is conjugated to both carbonyl groups, both the ketone carbonyl and the ester carbonyl. You'll notice I've also cleverly picked one where there's not even a stereochemical issue, right? That there's no E and Z possibility with that alkene. If there were a possibility, then you want to avoid, you'd use the same instincts you'd always use for figuring out which is the most stable possible of all alkene products. And you're on solid ground predicting that is the major product. And if you need to judge between the size of 2 groups, because you don't want to put the 2 bigger groups on the same side of the alkene, Well, in general, I think you can get away with considering that the larger of the two groups, let's say we were comparing these two, is going to be the one with more atoms in it. It's not quite true. It's kind of an oversimplification, but I don't think it will lead you astray. I think you'll be fine using that as your criterion. I mean, of course, assuming there's that one group doesn't have a whole bunch of iodines or some big fat atom like that. But other things being equal, I think you're probably going to be in good shape, assuming that the bigger of any two groups is going to be the one with more atoms in it. And it's not exactly correct, but I think that's going to be close enough. That and some common sense will get you through. Good. So that's another way of making sure that you get a clean mixed aldol reaction. One is choosing one of your reacting partners to have no acidic protons in it. And the other way is choosing one reaction partner that has an especially acidic set of protons, like this one here. In those two cases, you can get a clean reaction in general and get just one product. But if you were to mix like this guy with cyclohexanone, that would be doomed from the beginning. You'd get a horrible mess in that one. These two, I think, would be pretty clean. Good, that's all I can think of to say about that. Where are we at? 12:30, so we have till 12:50. We're making good time. Questions on these reactions that are in your class notes? And by the way, if you want to start working on this mechanism, that's another example of a mixed aldol reaction, and see if you can come up with a rationale as to why this is the major product and not the one resulting from condensation at what we would have expected to be the thermodynamic site. But I think you'll only get a stable product by deprotonation at the kinetic site, even though we're using a quote thermodynamic base. And I think there's a very good reason for that. It's very logical. Good, okay. So hopefully you came up with something like this. We'll start by deprotonating. And again, we would normally consider the kinetic site with our ethoxide ion. And again, can it deprotonating the thermodynamic site? Of course it can. It can and does. But that's why we don't see much, if any, of this compound, because I think if you stare at the structure, you'll see that this one cannot dehydrate. There are no protons beta to the oxygen. That carbon is quaternary, and in a way, so is the carbon in the benzene ring. So it's impossible to dehydrate. So you'll form this compound plenty. It's just that nothing can happen. In the end, what happens is this reaction goes in reverse. You pull the proton off, then the benzaldehyde falls off, and you go back to the starting material. So I would be shocked if you got any reasonably detectable amount of this stuff. All those steps are going to be reversible, and this will just revert back to the two starting materials. However, if you get reaction from the less hindered position, where are we at now? So here's our 2-methylcyclohexanone enolate adding to, ooh, I forgot an arrow. Shame on me. Adding to the enolate, something like that. And again, you could have also drawn the minus charge on this carbon. That's also fine. Perfectly acceptable way of drawing the mechanism. And once you've done that, we'll get this initial adduct. That then can pick up a proton from whatever the solvent is, which in this case is ethanol, and you'll get this beta hydroxy species. And this one now can react further because now we've got a proton, alpha to the carbonyl carbon and beta to the OH group. So now we're going to be able to dehydrate. And there's going to be a tremendously huge driving force to do that, once again, by an E2 mechanism, I'm sorry, E1CB mechanism. And so, almost got me with that one. And so as a result, once you've pulled off your proton, that's the first step in our E1CB. Second step is loss of the leaving group. And once again, there's at least 2 good resonance forms for this. You could put the minus charge in oxygen or on carbon, whichever you prefer. They're both perfectly acceptable. But however you draw it, the second step, which is going to be our rate determining step, our slow step, is loss of our leaving group. And not surprising that it'd be slow. Hydroxide's a pretty bad leaving group. So once we do that, again, once we do the dehydration, we get a new carbon-carbon double bond. And now if you look at it once again, we've got an extended conjugated pi system all the way through the benzene ring to the carbonyl carbon. That's all one extended conjugated pi system. That whole part of the molecule is flat. It's all of those atoms are sp2 hybridized. And so I predict that's going to be the major product. And as I mentioned before, I feel pretty good predicting that let me get this right now, I always confuse them, the E stereoisomer of the alkene is going to be more stable than the Z stereoisomer. So I feel pretty good about my odds in predicting that that's going to be the major product. You will get also addition on the other side, but that reaction is what we call unproductive. There's no way to get to a nice stable place from this one, so it simply reverts back to the starting materials. Whereas once we lose water, that's now irreversible, right? Because essentially you get a water molecule. Ultimately, you've got H and OH, so essentially you get water. Those are now going to be diluted in this ocean of ethanol. And those species are now a non-factor. It's not going to be possible to revert once you lose the hydroxide. And so I think that's going to be the major product. So again, I would recommend not thinking of this as an exception. It's yet another example of more of the same. And so I would answer the question, why is it that you get this as opposed to that compound? Well, because this guy can't dehydrate. So there's no pathway to a stable compound. And so every time you get one of these molecules, it just reverts back to starting materials. The benzaldehyde falls off and you get to try again. But once you get down here and you dehydrate, now it's no longer reversible. So that's why I would predict that you would get this as the major product. Make sense? Questions on that issue? Hopefully you got the mechanism. All right, well, there's just 2 more things I want to cover in our remaining 10 minutes. One is I would like to make you guys aware of the possibility of aldol reactions to be intramolecular, which is a word we've used previously. I don't want you thinking of this as a separate thing that you have to know. It's just another example of the same thing. But surely you can have an intramolecular reaction if in so doing you form a 5 or 6 membered ring. And I think you'll find, I've here numbered the carbons like this. I would say if you're a visual learner, you might find it helpful to write in the numbers, like just any arbitrary set of numbers, just so you can keep track of what carbon goes where. But I am not a visual learner, and I still will generally do that. It's pretty helpful. It's not mandatory, but I think you'll find that helpful. So, we can address all kinds of questions here. How do I know to deprotonate at the CH3 rather than at the CH2? Well, if you deprotonate at the CH2, you're going to get a 3-membered ring. Does that sometimes happen? Yes, but I think you'll agree a 5-membered ring is way better, a lot more stable. So no wonder we deprotonate at the methyl carbon. Of course, we could have deprotonated here and added to that oxygen. It's the same thing. So that would be another one that would be worth working out on your own. See if you can convince yourselves that you get this cyclopentenone derivative and close a 5-membered ring followed by E1CB dehydration and formation of this product. And I think you would get that in very high yield. And if there were one more CH2 here, I'd predict you'd get the same type of thing, but with a 6-membered ring. So anytime you can close a 5 or 6-membered ring, that's always a very low energy pathway because it's intramolecular. you're no longer depending on the right molecules to collide with enough speed, enough kinetic energy to react, and also in the right orientation. You don't have to depend on that because everything's right there within the same molecule. And we've already spoken about 5 and 6 member transition states. Those represent very low energy pathways. So I think this reaction would be no problem. I'm just using this compound though as an example. I used hydroxide and aqueous ethanol just for the example. Any other reasonably strong base would do. But this is not a different reaction from what we've been studying. It's the same thing. It's just going on within the same molecule. Good. Make sense? Okay. Well, the only other thing I want to talk about today is the Claisen condensation, which I like to think of the Claisen condensation as an aldol reaction with esters. Period, full stop. There's otherwise no difference. They can undergo the same type of reaction, and the mechanism is in many ways more straightforward because there's no possibility for dehydration. So I hope to convince you of that when we go over the mechanism of 2 ethyl acetate molecules coming together to make ethyl acetoacetate. I'll probably go over at least some of this next time too, but I want to make you aware, just as with aldol reactions, you can have mixed Claisen reactions, just like you can have mixed aldols. You can have intramolecular Claisen reactions, just like you can have intramolecular aldol reactions. An intramolecular Claisen condensation is often called a Dieckmann reaction. I don't think I care very much if you know that, but it does have a name. But let's save those details for next time, since we only have about 6 minutes. So here we're treating ethyl acetate with some base, and you'll notice that in fact, just as before when we did this reaction, this mixed aldol reaction, this is kind of a Franken reaction because it's sort of a mixed aldol Claisen type thing. But whatever it is, it's the same type of carbonyl condensation reaction involving deprotonation, alpha to a carbonyl. But you'll notice here too, just as we did in chapter 22, when we talked about the acetoacetic and malonic ester syntheses, we were very careful to match the ester and the base and the solvent so that they all matched. Because if you don't, then you're going to wind up scrambling the ester, and we want to avoid that. Remember, it's not that the ethoxide ion doesn't attack the ester carbonyl. It most certainly does. It will attack this carbonyl too. It will attack the one on cyclohexanone also. All those things are happening. They're just not productive steps. Once that attack happens, in the case of the 2 ketones, the only thing that can happen is the ethoxide ion falls off and you go back to the starting material. Or in the case of ethoxide ion attacking the ester, draw out the ester functional group, if that makes it easier for you to see. But you'll notice that now you have a carbon that can lose either of 2 ethoxy groups. Ethoxides is leaving group. It doesn't matter, they're the same. So it's not that the ethoxide ion doesn't attack the ester, it absolutely does all the time. It's just there's no consequence of that chemically. It doesn't affect the reaction outcome. And so same thing here. In a Claisen reaction, you want to make sure that your ester and your base and your solvent all match so that you don't scramble the ester. The reaction does produce at first an enolate ion, since we're in an alkaline medium. So at the end of the reaction, you do need to carefully, slowly, respectfully add dilute aqueous acid. You want to be very, very careful with that so you don't hydrolyze the ester. But as long as you're careful, that's not such a big deal. Just add it slowly and maybe in a cold bath or something like that. And you would have, in this case, 2 molecules of ethyl acetate coming together to make ethyl acetoacetate. And so that would be a typical non-mixed Claisen condensation. And we'll go over mixed ones later and intramolecular ones later. That can wait until Wednesday. But first step is just like with ketones and aldehydes. You just deprotonate alpha to your carbonyl. except in this case, it happens to be an ester carbonyl instead of a ketone or aldehyde carbonyl. No matter, you can form the enolate of an ester. That's no problem. Once you've done that, here's the enolate of your ester. That's now going to find a second ethyl acetate molecule and add to it. Remember, again, this is not going to be it's not going to be either, what should I call that? It's not going to be an SN2 reaction or SN1 for that matter. This doesn't just come in and kick out the ethoxide. No, remember, we have to go through our tetrahedral intermediate. So that's this over here. And this is where in an aldol condensation, we'd look to put a proton in this oxygen and then think in terms of dehydrating. That's a moot point here. You don't even have to worry about that with Claisen condensations because this carbon now has a good leaving group on it, or at least a leaving group that's good enough in base. If this had been a ketone or aldehyde carbonyl instead of an ester carbonyl, we wouldn't have that option. Then we'd think of dehydrating. But here we can simply reform the carbonyl by kicking out the ethoxide leaving group. And again, only in alkaline conditions can we rationalize losing hydroxide or an ethoxide ion as the leaving group. That's not going to happen in neutral to acidic medium. But alkaline medium, you can rationalize that. You're close enough within those pKa values that you're in good shape. And so it's at this point that we might be tempted to say, well, that's my product. We're done. I can stop now. No, you can't. Because as has happened so many times before, we've generated this molecule in the presence of base. So there's still ethoxide ion floating around. And the silly comment I used to make in this case was, in front of my class, I especially did this at my previous school, is we're going, excuse me, all y'all molecules down there, can I have your attention, please? Please do not deprotonate over here, okay? Because if you do, then I have to write another step in the exam and it'll take me time. They don't care. Molecules do not care how we feel. They're quite cruel in that regard. So there's no way you can prevent the already present ethoxide ion from pulling off one of those two protons now that's alpha to both carbonyls, both the ketone and the ester carbonyl. So you can't prevent getting the enolate. There's no way you can add the acid quick enough so that you don't have to draw this, don't have to show this. If you did, then you'd get an incomplete reaction. So remember what this means when we number steps. Here's another way of thinking about it. Remember, this means that we add whatever is past number one, and we wait until everything's done reacting and nothing further can happen. And then we add what's after number two. And that's the case here. So this is going to keep reacting since you can't prevent it. So we'll surely pull off one of those protons. We'll surely get an enolate. This is only one of at least three correct ways to draw this enolate. You could also have drawn the minus charge on this oxygen. You could also have drawn it on the carbon. Any of those three resonance forms is fine. However you slice it, once you get to that enolate, that's what's going to be floating around in the reaction vessels, swimming around very happily, watching the scenery until we again very carefully add dilute aqueous acid. The first thing the aqueous acid is going to do is, of course, kill off any remaining ethoxide ion. Once that's accomplished, then it's going to start putting the protons onto the enolate. And of course, it will put it onto the carbon. You'll get the keto form of that one. But yes, you do want to add this very slowly and carefully, and probably at a reduced temperature, so as not to hydrolyze the ester. We talked about that reaction in chapter 21. So this is not where you get a bottle of concentrated HCl and pour it in. No, this is, I don't think I've ever done a Claisen condensation, but I would do this very carefully. I'd keep the flask nice and cold, use nice dilute acid, maybe dilute sulfuric acid, maybe dilute HCl. And I'd probably be there with my pH paper, you know, making sure that I don't go below about pH 6 or something like that. But if you're careful, then you will isolate the Claisen condensation product. What happens if this reaction is intramolecular or if the two reacting partners are different? That's Wednesday. That can wait until Wednesday, and we'll finish the chapter then. So other than that, I'm out of time. Have a great day, and I will see you all on Wednesday.